So in the nervous system, a lot of the communication that is done among nervous system cells is electrical. That is, some change in the electricity down the length of a cell, like down the length of an axon of a neuron, is going to be a way for the cell to conduct information. So this lecture is about setting up the foundational knowledge for us to understand that there is in fact an electrical difference between the inside of the cell and the outside of the cell. So when we've looked at potential energy, we have so far focused our efforts on chemical energy. And we've looked at concentration gradients as being a type of chemical energy. But electrical gradients are also a type of potential energy. And electrical gradients can occur when there is an uneven distribution between the intracellular fluid and the extracellular fluid of ions. So remember, ions are going to carry a net charge. And the ions that are most likely to move between the intracellular fluid and the extracellular fluid, and therefore create that difference of electricity, are going to be one of the following: sodium, potassium, chloride, or calcium. So if I were to take an electrode and place it into the intracellular fluid, and take another electrode and place it in the extracellular fluid, and then hook that up to some sort of reader that measures the voltage, which is the electrical difference between the two, I would in fact find out that they are different. The electrical potential of those two environments is different. And so that difference is referred to as the membrane potential. So when we talk about the membrane potential, we're really talking about across the plasma membrane, so that's the membrane, and the potential energy associated with the difference in electrical charge. So I said a mouthful there, and hopefully it will become more clear as we move on in this lecture. But the membrane potential refers to, again, potential energy across the plasma membrane. So really what that means is between the extracellular fluid and the intracellular fluid because of some sort of electricity, which is going to be due to some difference in charge from these ions. Okay, our goal is going to be to establish what is called the resting membrane potential, and we'll be doing that in a little bit. Before we do that, we need to take a look at some other things. First of all, we need to understand that the distribution of the ions that I've listed here is not equal in and out of the cell. So what we're going to do first is we're going to compare the relative concentrations of sodium, potassium, chloride, and calcium between the extracellular fluid and the intracellular fluid. If you're drawing this out with me, go ahead and get a sheet of paper, maybe half a sheet of paper, and draw out my axon. So the brown line there is going to be a plasma membrane. I have another plasma membrane on this side. So this is the intracellular fluid and the extracellular fluid. I am going to give you the approximate concentrations of the different ions. I do not expect, if you're in my class, that you will memorize these numbers. However, you are expected to know which compartment has a greater concentration. So if I'm talking about sodium, the extracellular fluid has a lot more sodium than the intracellular fluid, and you definitely will need to memorize that. The actual millimolar concentrations are not going to be things you'll need to memorize. So I'm also going to use font size to try to convey the difference in concentrations. So for sodium, the extracellular fluid has usually somewhere around 145, it's usually between 140 and 150 millimolars of sodium. So I'm writing that in really big font so that you know that's actually quite a lot. Where the inside of the cell has something more like 15 millimolars of sodium. Now, why does the extracellular fluid have so much more sodium than the intracellular fluid? That is because of the sodium-potassium pump, which continually kicks sodium out of the cell. Remember, the cell says nah to sodium. And the sodium-potassium pump brings in potassium. Remember, K is a keeper. So we would expect that the intracellular fluid has a lot more potassium than the extracellular fluid. And in fact, the intracellular fluid tends to have around 150 millimolars of potassium, where the extracellular fluid has closer to 5, so really small. Now there are two other ions of significance, one of which is chloride. Chloride is also concentrated in the extracellular fluid. So one way that you can remember that chloride is concentrated in the extracellular fluid is that sodium and chloride make up table salt. So when you think about salt, chances are you think about sodium chloride. Sodium and chloride go together like two peas in a pod. So wherever sodium is, there's chloride. So chloride always likes to stick with its little buddy, sodium. So chloride is not very common inside the cell. Okay, calcium is not very concentrated relative to these others. So when we're looking at calcium, calcium is in fact concentrated in the extracellular fluid, but even that isn't very much. So there's approximately 1 millimolar of calcium in the extracellular fluid, and there's considerably less than 1 millimolar of calcium in the intracellular fluid. So I'll go ahead and zoom in a little bit here. Again, these are not numbers you need to memorize. You just need to know which compartment has the greater concentration of the particular ion, extracellular fluid or intracellular fluid. So now that we've drawn this out, let me go ahead and show you a graph that basically shows what I drew. Here I have different ions. Here is a concentration that's in millimolars. And you'll notice that plasma and the interstitial fluid are both types of extracellular fluid. That was covered in a previous lecture. So we would expect that my salmon colored bar and my lavender colored bar would be about the same height because there's a lot of movement of fluid between the plasma and interstitial fluid. So typically the ion concentration in the plasma is very similar to the ion concentration in the interstitial fluid, both of which are types of extracellular fluid. Whereas the intracellular fluid is going to be very different. So when we look here at sodium, you can see that the extracellular fluid has all of the sodium, where the intracellular fluid has very little. When we look at potassium, it's the converse. The extracellular fluid has very little potassium, and the intracellular fluid has most of it. Again, chloride likes to be with its little buddy, sodium, more concentrated in the extracellular fluid. Because bicarbonate and other large anions and proteins don't really move across the membrane, they don't contribute significantly to the membrane potential, and therefore we're going to ignore them. So again, if what I just said doesn't make a whole lot of sense, hopefully it will later on. The takeaway at this point is that this is not information you need to focus on. So I mentioned that these ions, sodium, potassium, chloride, and even calcium, will move across the membrane. How will they move? Most of the time they move through channels that are specific for that particular ion. So let's take a closer look at the channels. You can have channels that are open or gated. And typically channels, it's not true 100% of the time, but typically channels are going to be specific for one ion. So if you are a sodium channel, then you only let sodium through and not potassium, not chloride, not calcium, etc. If you are a calcium channel, then you only let calcium through, not sodium, not potassium, not chloride, etc. So we will often describe the type of channel by what ion is allowed through. Moreover, Channel proteins are either built to be open all the time, sometimes these are referred to as leak channels, or they are built with a gate, and we call those gated channels. So if I have an open sodium channel, it's going to look like this one. And if I have a gated sodium channel, it's going to look like this. Now, the importance of the gated channel is that it can open and close. When the gated channel is closed, no movement of ion is permitted through the channel. When the gated channel is open, then the ion is allowed to move. So what opens or closes the gate? Well, it turns out that there are kind of three triggers, or three possible triggers for these gated channels. Each gated channel is built to respond to only one of these triggers. So this is not a pick and choose, what do you want to respond to today? You are built to respond to only one of these three stimuli. And one of the stimuli is a change in voltage. So these are referred to as voltage sensitive gated channels. So a change in voltage means that there has been some other change in ion movement or relative electrical charge, and that change is going to open the gate or close the gate. For the next couple lectures, we will focus exclusively on voltage-sensitive gated channels. But before we are done with Exam 1 module, we will see all of the gated channels, so we should look at the other two right now as well. Some gated channels are opened or closed by a chemical that binds to that channel. We actually got a little bit of a look at this in a previous lecture. So let me go ahead and write this out. And now let me show you that image from a previous lecture. In a previous lecture, we saw that certain receptors were in fact gated channels, and that when that ligand binds to that little notch there, it would open the channel. So this, as drawn, is an example of a chemically gated channel. The channel flap opens and or closes in response to a chemical that binds to it in a little notch. All right, our final type of channel is one that responds to some sort of mechanics, something mechanical, some physical force, movement, etc., pressure. So in other words, these channels are physically being opened and closed by some sort of force. As an example, imagine if I had some sort of string attached to that channel and I yanked it. That would be an example of mechanical motion. I'm mechanically opening that channel. So these are mechanically gated channels. So those are the three classes of gated channels. They can be opened by a change in voltage, the binding of a specific chemical, or some sort of mechanical force. But once again, each gated channel is built to respond to only one of those stimuli. If you are a voltage-sensitive channel, you are not also a mechanically gated channel, etc. And then the other way that we classify these gated channels is by what they let through. So if I were to say this phrase, voltage-sensitive sodium channel, you would know that this is a channel protein that specifically lets through sodium. The gated is implied because I'm describing it as voltage sensitive, meaning that the gate is going to open or close in response to some change in voltage. So now that we've introduced some basic concepts that will be necessary to understand concepts introduced later in this lecture and other lectures, let's come back to that membrane potential idea. So the membrane potential is again an electrical difference between the inside of the cell and the outside of the cell. And it is measured typically in millivolts. So it's not so great to be a full voltage, but it is substantial enough to register as millivolts. And typically the way this is done is with two electrodes, one inside of the cell and one outside of the cell, and then you measure the difference. And you can see here that the difference is registering at minus 70 millivolts. As we are going to see, it turns out that minus 70 millivolts is kind of the default position that our neurons take, meaning that the inside of the cell is more negative than the outside of the cell, and the inside of the cell registers minus 70 millivolts relative to the outside of the cell. Now, if you're thinking, what? I didn't process all that. Don't worry, we'll get back to it. But do know that this number was not selected randomly. We're going to see this number come back. So now let's kind of step back and take a look at what does it mean to be a difference in charge. So I have two beakers here. I have a blue beaker and a white beaker. And I'm using extremely simplified examples, but basically these examples demonstrate the difference between a chemical disequilibrium and an electrical disequilibrium. So another way you can think about this is a chemical gradient or an electrical gradient. Equilibrium suggests equal, that there are equal concentrations or equal charges in both beakers. But here you can see that the concentration of potassium is not equal. There are 3 potassiums here, and there is 1 potassium there. So are these beakers in chemical equilibrium? The answer is no, they are not, because I have 3 and 1. That's not identical. If it were 3 and 3 or 2 and 2, then they would be in equilibrium. But as it's drawn, they are in chemical disequilibrium. What about electrical? Do they have the same net charges? Well, since each potassium carries a +1, my blue beaker has 3 positive charges, and my white beaker has 1 positive charge, so they are also not in electrical equilibrium. They would be in electrical disequilibrium. Let's take a look at this example. Here, I have a blue beaker with 2 potassiums and a white beaker with 2 sodiums. Those are not chemically the same. So these are not in chemical equilibrium, but they are in electrical equilibrium, because here I have a +2 and here I also have a +2. So the answer to the other question is yes. Assume for a moment that my protein has a net charge of -1. So there's my protein, and I have 2 of them. Are these beakers, the blue beaker and the white beaker, in chemical equilibrium? What do you think? No, there's nothing about these that are the same. To be in chemical equilibrium, I would need the chemical composition of one beaker to be identical to the other beaker. So the answer here is no. Are these beakers in electrical equilibrium? Yes, they are. The net charge in this beaker on the left, the blue beaker, is actually going to be 0. I have 2 positive charges and 2 negative charges. +2 - 2 = 0. The net charge over here is also 0. So because they have the same net charge, they are in electrical equilibrium. Okay, this compares 2 beakers in a very simplified example. Let's take this concept of chemical versus electrical equilibrium and overall net charge and take a look at what happens when we compare 2 of these beakers and we set one of them to 0. So consider this setup. I now have my blue beaker and my white beaker right next to each other. In my blue beaker, I have 3 potassiums and 1 phosphate group, and my white beaker, I just have a single sodium. So the first thing we need to do is we need to add up all of the charges in each beaker for our net charge. So in my blue beaker, what's my net charge going to be? Well, I have 3 pluses, but I also have a single anion that has a -3 charge. So +3 - 3 is 0. And this one, my net charge is +1. Okay, I'm not interested in the overall net charge of each of these. I'm only interested in the difference in charge. And in order to figure out the difference, I have to set one of these as my baseline, my 0. And in my example, I'm going to set my white beaker as my 0. Now, what does that mean, to zero something out? I want you to imagine for a moment that you're working with a chemistry scale, and you put something like, oh, I don't know, a mouse on top of it, and then you push the tare button or the 0 button. Now, the mouse is still sitting on it, but it's registering as no weight, 0 weight. So if you add a pencil on top of it, then you're only measuring the weight of the pencil because it was already tared out or zeroed out with the mouse. If I take the pencil off but leave the mouse on, my weight will read as 0. Is the weight actually 0? Is the weight of the mouse 0? No, but I set the weight of the mouse to be 0. If I take the mouse off, what happens to the mass or the weight? It goes into negative territory, right? You see that number go from 0 to like minus 10 grams. And you go, oh, is the air really minus 10 grams? No, but relative to the weight of the mouse, once you took it off, it went into negative territory. So in the same way, we're going to set one of these beakers as our 0, and then we're going to measure the charge of the other beaker relative to that 0. So if I'm setting this as 0, then what I need to do is subtract -1 from both sides. So that will give me 0 here, but it will give me -1 here. So the way that this would be read by a voltage meter is, if I set my white beaker to 0, my blue beaker reads as -1, which might seem a little strange because technically it was 0 net charge, but now it's reading as -1. And all that's saying is, well, relative to the white beaker, there's 1 negative charge difference. Now, what I set to 0 is somewhat arbitrary. I could have easily switched these around. If I had instead set my blue beaker as the 0, then my voltage meter would read as +1. The default way that we measure the difference in electricity between the extracellular fluid and the intracellular fluid is to set the extracellular fluid as the 0. The extracellular fluid is always going to be the 0. You will always set this as 0. And so what you are actually measuring on that voltage reader is the net charge in the cell relative to the extracellular fluid. The extracellular fluid is 0, and then the cell is what compared to that? Well, you can see here that -70 seems to be the answer. That is to say that the inside of the cell seems to have more negative charge than the outside of the cell. Most of our cells have a membrane potential that is more negative than the outside of the cell. So now that we've explored that, let's take a look at how the membrane potential is in fact truly set up in our cells. All right, if you're going to draw this out with me, I encourage you to pause the video and go ahead and copy this down. I have a cell that has 6 potassium ions and 2 phosphate groups, each with a -3 charge. What is the net charge in the cell? And as it's drawn, the net charge is 0. What is the net charge outside of my cell as it's drawn? There are 6 sodiums and 6 chlorides, so therefore the net charge is also 0. So as it's drawn, the intracellular fluid and the extracellular fluid are going to be in chemical disequilibrium, meaning the chemical composition of the extracellular fluid is not identical to the intracellular fluid, but they are in electrical equilibrium because the net charge in both cases is 0. It turns out that the sodium-potassium pump is going to be instrumental in setting up the chemical gradient that you see here. by kicking out most of the sodium and bringing in most of the potassium. But most of these cells also have leak channels. And one leak channel that's particularly common is for potassium. So let's go ahead and draw in a potassium leak channel. That means that it's going to be an open channel. So the only ion that will be allowed to move is potassium. So which way will potassium want to move? Of course, potassium is going to want to move out of the cell. Why? Because it is concentrated in the cell and it wants to diffuse down its concentration gradient until it reaches equilibrium, right? Mostly. Here's where things get a little strange. As potassium starts to leave, we actually do in fact predict that we would have 3 potassiums out of the cell and 3 potassiums in the cell if potassium reached diffusion equilibrium. But it turns out that not all of the potassium we expect to leave actually does leave. Why? Because there are 2 competing forces at play. Chemically, potassium is drawn out of the cell. But let's take a look at what happens to the electricity when we move potassium out of the cell. If I move one of these potassiums out of the cell just like that, just one, my net charge is no longer 0. My net charge in my intracellular fluid is now -1, and my net charge in my extracellular fluid is now +1. So it turns out that the movement of even one ion from the intracellular fluid to the extracellular fluid throws the electrical balance into disarray, and we are no longer in electrical equilibrium. In fact, remember, we always set the extracellular fluid as our 0, so the way this is really measured, we have to reset this as 0, so we're going to subtract 1 from both sides, and the way this is going to be measured is as a -2 for the cell. So the voltage reader will pick up the exit of a single potassium ion as actually a -2. Okay, let's move another potassium ion out. How will the voltage reader read the ICF now? It's going to read it at -4. My nets are going to be now +2 for extracellular fluid and -2 for intracellular fluid, but I'm going to subtract -2 from my ECF to make it my 0. I'm going to 0 it out, which means I have to subtract the same thing from my intracellular fluid. So it's going to read the movement of 2 potassium ions exiting the cell as a -4. Again, a big change for just a small amount of ion movement. So now what's happening? The cell is becoming much more negative than the extracellular fluid. And what is attracted to negative things? Positive things. So now this potassium is kind of caught between 2 opposing forces. Chemically, it wants to move out of the cell. But electrically, it's a positive charge. And you know what? There's a lot of other positive charges out here. It doesn't like being with all these other positive charges so much. So it wants to actually get pulled back into the cell electrically. So the pull chemically is out of the cell, but the pull electrical is inside of the cell. And so as a consequence, potassium never reaches its chemical equilibrium, but rather seems to stop somewhere in between, kind of like this, where some of the potassium exits, but as we try to get more potassium to exit, it usually comes right back in because the electrical pull at that point is too strong and it pulls potassium back in through that channel. So this is really interesting. So far, we've only looked at gradients from a chemical standpoint, and we've tried to predict the movement of things due to their chemical gradient. But ions respond to two different gradients. They respond to both their chemical and their electrical gradients. So sometimes the combination of this is referred to as the electrochemical gradient. And again, they're not always in the same direction, as we see here with potassium. Now what I've drawn is also shown in the book's images, and we'll quickly go through those. So these are images directly from your textbook. They're showing the sodium and the chloride concentrated in the extracellular fluid, and potassium and other negatively charged ions, don't worry about what those are, in the intracellular fluid, the point being that the net charge as drawn is 0 and 0. But if I put a potassium leak channel in there, some potassium is going to want to leave. Now again, we would predict, based on this image, that 2 potassium ions would exit the cell and enter the extracellular fluid. But it turns out that because the electrical gradient is going to pull potassium back in, we don't actually see that much potassium leave. There are equations that allow you to predict the voltage of the intracellular fluid, again relative to the extracellular fluid, which is always set at 0, if one of the ions is allowed to reach its electrochemical equilibrium, meaning wherever it finds its kind of settled spot in between these two opposing forces, if a channel protein or if sufficient channel proteins are available for that particular ion. So this is referred to as the Nernst equation. And for my class, you are not required to know the Nernst equation or calculate the Nernst equation. However, it is useful to know this. If potassium is allowed to reach its electrochemical equilibrium, then the intracellular fluid will measure at minus 90 millivolts. So that seems to be where the settling point is. Now, what about the other ions? Could we calculate, the electrochemical equilibrium for the other ions? And the answer is yes. Let's conceptually think about what would happen if I traded out my potassium channel for a sodium channel and let sodium reach its own electrochemical equilibrium. Well, chemically, sodium is going to want to come into the cell, right? And as sodium comes into the cell, positive charge comes in with it. So this is now +2, and this is -2. So you can see that the same situation is encountered by sodium, where chemically sodium is drawn into the cell, but as positive charge starts accumulating in the cell, sodium kind of starts looking longingly back over here and going, but wait, it's more negative out here now, and I don't want to be concentrated so much in here. Maybe I want to be a little bit more out here. So the Nernst equation predicts that where sodium finds its happy compromise between the chemical gradient going this way and the electrical gradient pulling it that way at about +30. Okay, so why am I bringing up the Nernst equations and their outcomes? Because they're instructive as we start to look at the true resting membrane potential. In the neuron, the resting membrane potential is -70 millivolts. The term rest or resting is important. What that means is if no gated ion channels are opening or closing, and all we have is the sodium-potassium pump and leak channels, which are always open, the resting membrane potential will settle at -70 millivolts. Notice that's closer to the Nernst equation's prediction for potassium than it is for sodium. That's important. So now that we've looked at all of the different pieces of the story that contribute to establishing the resting membrane potential, let's try to put it all together into one cohesive story so that you can truly understand why the resting membrane potential of a neuron is in fact at minus 70 millivolts. Our story starts with the ubiquitous sodium-potassium pump. The sodium-potassium pump sets up the chemical gradient that's going to drive the movement of ions in the first place. So it kicks out sodium and brings in potassium. By itself, the sodium-potassium pump does not contribute substantially to an electrical difference. There's probably a small contribution because 3 positive ions are going out and only 2 positive ions are coming in. So for every turn of that sodium-potassium pump, we do end up with a slightly more negative cell, but we kind of ignore that. That doesn't seem to be substantial, so we just ignore that. The importance of the sodium-potassium pump is setting up the chemical gradient between sodium and potassium. So with the sodium-potassium pump working, we set up a very strong chemical disequilibrium, but there's minimal electrical differences at this point. The intracellular fluid and the extracellular fluid are not substantially different in their electrical charges. Okay, every neuron has a fair number of potassium channels that allows potassium to get very close to reaching its electrochemical equilibrium, which, remember, based on the Nernst equation, would be at minus 90. So if this was our entire story, then the resting membrane potential would be minus 90, because that's where the electrochemical equilibrium is for potassium. But it turns out that there are a handful, not very many, about 40-fold fewer, in fact, than potassium. But there are a handful of sodium leak channels also embedded in the membrane. So potassium is allowed to pretty much do whatever it wants until some of the potassium exits and the inside of the cell is more negative. Remember that sodium wants to come into the cell, but sodium has a very difficult time finding a way into the cell because there's just so few channel proteins. So there's just not a lot of opportunities for sodium to trickle into the cell. However, a tiny amount does. So a little bit finds its way into the cell, and it is enough that the resting membrane potential is brought to be a little bit more positive than the minus 90 floor. It's a little bit higher than that, offset by a little bit of sodium coming into the cell. And so that with that little bit of sodium coming into the cell, the overall resting membrane potential is minus 70. So one of the ways that I remember that there's not a lot of sodium channels is that Na also stands for not a lot, so rare. The resting membrane potential is a combination of the sodium-potassium pump and the ratio of potassium and sodium leak channels. So what I'm saying is that if you started to vary the relative ratio of sodium and potassium leak channels, you would change the resting membrane potential of that cell. And again, it's all driven by that sodium-potassium pump setting up the chemical gradient in the first place. So what do I mean by that? Well, imagine if the cell only had potassium leak channels, no sodium channels. Then the resting membrane potential would be minus 90. What if the cell had only sodium leak channels and no potassium leak channels? Then the resting membrane potential would be plus 30. So what if the cell had half and half? Half sodium, half potassium means equal proportions. We would expect the resting membrane potential to be somewhere between the plus 30, which is exclusive of sodium, and minus 90, which is exclusively potassium. So we would expect it to be somewhere in the middle there, somewhere around minus 30 or something like that. The resting membrane potential of a neuron is in fact minus 70 millivolts. Not all cells have the same resting membrane potential. In the human body, you can change the resting membrane potential by changing the proportion of potassium and sodium leak channels respectively. That's where we're going to end this lecture. We'll pick up the next lecture by looking at graded potentials and action potentials. I'll see you then.